All right, I'm going to go ahead and call this video How to Put NFTs on Bitcoin in a Way That Doesn't Piss Off Bitcoiners and Yet Allows NFTs on chain to be cheaper, faster, and more efficient. Basically, no bloat, so the Bitcoin network and Bitcoiners won't be going crazy, and yet NFTs can still be allowed on chain. Because at the end of the day, it's like a lion that's got a taste of man flesh. They're not going away. NFTs aren't going anywhere, and they're certainly not going to leave Bitcoin alone. So if we're going to do something, let's try to do it correctly. All right, so first, in order to even understand how, I'm going to give an overview of how Taro works, but it could be any protocol. This is just one that's coming out. There's plenty of other protocols, Web 5 protocols that are going to use this same type of technology, but it's all rooted in Taproot, no pun intended. And since everyone on Twitter seems to have no idea really what Taproot does, we need to do a really quick overview on what the heck Taproot is. So the first thing we need to understand is about Merkle trees, and I'll give the example as far as how it's used for scripting. So very shortly, wallets are going to have tap script enabled. I believe Nunchuck in the next month is going to have it, along with Ledger Wallet and along with all wallets after that. So we're going to be able to create complex spending paths where we have multiple conditions. Basically similar to what Lightning uses, but we can create it ourselves. So I just made this one up, like what if you have a 3 of 3 multi-sig with your business partners? But obviously this is dangerous because what if someone loses their key? Not a big deal because you have a fail-safe condition. After 3 months, you can make it 2 of 3 business partners. And you know what? What if two business partners die in a car accident? Well, after 6 months, you can do 1 of 3 business partners plus the lawyer's key. All right. And if that all fails, after 1 year, you can do 2 or 3 of the lawyers from the law firm. Just completely just made this up. The whole point of this is in an overview, when you have a script like this, all these conditions are hashed and they're changed to an address, and that's actually what you pay to. This is a pay to script hash. So you're paying to a hash. What is that hash? That hash is a script that has a whole bunch of conditions. When spending the funds, the entire script needs to be revealed, and the chosen path needs to be successfully executed. Long scripts take up a lot of space and are therefore expensive. They're also not private at all since the entire script is published onto the blockchain. So that's the first problem we're going to try to solve is I don't want to have to reveal everything. If I'm just paying with my best case scenario, 3 of 3, the world doesn't need to know about all this. This is my private business script. This is my private inheritance script. I don't want to share that. Well, if we instead break all those things up, and I changed it for a later example. I made it more like an inheritance protocol. So 3 of 3 after 6 months, 2 of 3 after 1 year, 1 of 3, and after 2 years, let's assume I'm dead and my wife can access the funds with her public key. Because she couldn't understand the instructions in my will. All right, let's just go with this. But we're going to break them up into individual pieces, and instead of hashing the whole script together, we're going to go ahead and hash everything individually. We're going to hash this one, this one, this one, and this one. And then we're going to take these two hashes and we're going to hash them together. Then we're going to take these two hashes and we're going to hash them together. Then we're going to hash these two together. And we're going to get the root of the hash tree. And this is what we're going to pay to. So why not? If we actually paid to the root of a tree like this, then the advantage would be that we only need to reveal the spending condition we're using and not the entire script the way it is now on Bitcoin. For example, if I was just wanting to use the 3 of 3 pub key, all I need to do is reveal this script, obviously, reveal this hash, and reveal this hash. Because anyone could hash these together to get this hash this with this hash in order to get this and prove, just like you can on chain now, that this condition was definitely a part of this Merkle tree. Now, nerd note, this is what we're going to refer to. This is what gets referred to in Taproot as a MAST or a Merkleized Abstract Syntax Tree. We'll just call it a Merkle tree for short. The next thing you need to understand, once you understand that, is what the heck Schnorr signatures do, Now I'm going to skip this for now, put a little background why, in case you're wondering why Bitcoin suddenly just up and left and stopped using elliptical curves and started using Schnorr signatures. You can get some background there. But the real important thing to understand is what they do. All right, so signatures are linear, allowing for signature aggregation. What the heck does that mean? For example, currently, if you want to do a 3 of 3 multi-sig on Legacy or SegWit, in order to spend it, you need to present all three public keys and you need to present all three signatures. If it's a 2 of 3, you got to do all three public keys and two signatures. But you have to present a lot of data because each public key needs to be signed by a private key, etc., etc. However, with Schnorr signatures, since it's linear, you can effectively add all the public keys together. So if we added pub key 1, 2, and 3 together, we would just get a new public key, pub key 1, 2, 3. Because in the end, pub keys are numbers. In the case of elliptical curve, they're the x point of a point on a curve. But with Schnorr, they're actually just numbers. So by aggregating them all together, you can do the same thing with the signatures. After the private keys sign, you can add up all the signatures and have an aggregated signature. So that means for Taproot, you could present just the aggregated public key and just the aggregated signature. So it looks identical. There's no way you can tell the difference if this is just a regular pay to public key, because that's what it looks like. You have a public key and you have a signature. Or if it's a 2 of 2, or a 3 of 3, or a 20 of 20, or 1,000 of 1,000, an N of N, any type of N of N multisig, since you can add them all together, there's no way to tell the difference on chain. So you have a major privacy increase. Now, of course, we don't just necessarily add them because there's security risk to that. But technically speaking, you could just add them. So for the sake of demonstration, we're just going to do addition and skip any more complicated math. So aggregating signature not only saves immense space, but it also makes it more private, since a multi-signature spend will look identical to a regular key spend. I just recently did a test case of what is the biggest valid transaction you can do, because everyone's going crazy about ordinals using up creating a 4 megabyte. I think if I did, I forgot the number offhand. It's like 3,500 and something. If you had 3,500 5 of 5 multi-sig inputs paying out to one output, if you did that using SegWit, it would the biggest it would use up all 4 million weight units, but it would come out to about 3.4 megabytes. That's like the most space anyone could do. Now, why anyone would do that? Obviously, only an exchange would be doing some type of big consolidation like that. But guess how big the Taproot transaction would be for the same one? It would only be 600 kilobytes. So it'd be much, much, much smaller, almost 4 times smaller, or 3 and a quarter, or whatever. So this solves a big privacy problem in Bitcoin, since address types make it easy for chain analytics companies to figure out what kind of transactions people are using. Once Taproot becomes mainstream and everyone starts using Taproot transactions, chain analytics, the government, whoever's watching the network, is going to have a much more difficult time figuring out what is what. They're not going to be able to tell the difference between a multi-signature and a regular one-to-one signature, among other things. Of course, we're going to add on to that as well. So the real question is, why not the best of both worlds? Currently we shown with Schnorr, if you have a 4 of 4, you could take those 4 public keys and create one aggregated public key, and that's what you actually show online. And you could spend using an aggregated signature. So as far as what the world sees, you've now hidden from view, you've obfuscated in a way, any N of N multi-signature and any regular payment. All right, now that's great, but we want more. All right, and again, we have no idea who signed. What about the script path? Because script paths are coming to our wallets very soon. They're already here with Lightning and with other protocols. What about our first spending condition? Remember, our first spending condition was a 3 of 3 multi-sig. Can we use Schnorr on that? Well, sure. Let's, for example, take this out of our tree and we're going to turn it into one public key. All right. So this is pub key 123. This is an aggregation of all these, right? But now we have two different things. We're either going to do Schnorr or we're going to pay to the root of a Merkle tree, to try to hide all the conditions in a script. Well, again, using the magic of Schnorr, by saying magic of Schnorr was a brilliant mathematician, and his stuff was patented, and it just got off patent by the time Satoshi was creating Bitcoin. So all the open source stuff was with ECDSA. So this is all new math that's available to us. You could combine the root and the public key to create a tweaked public key. This is the technical term actually is called tap tweak. All right. So for all practical purposes, let's just say we're just adding. We can add the root because remember the root is just a hash. It's just 256 zeros and ones, which we can read as a number. We can just add it to the public key and get a tweaked public key using tap tweak. This is actually what is on chain. So a taproot address does not pay to a hash. A taproot address is a pay to public key, and it's paying to this tweaked public key. Well, I'm calling this the taproot public key, tweaked public key. And that public key, as you now know, is tweaked from another public key and a root of a tree. It can be. Obviously, if you don't have any of these conditions, you may not use them. So in order to spend from a tweaked public key, we have two options, right? We can pay with just this public key, which you may be wondering, how the heck do you do that? Because this public key isn't on chain. It's a tweaked public key. It's a public key combined with this root. Nobody knows that. All anyone can see on chain is just a plain Jane public key. But our signature, we get our three business partners with three public keys. They use their three private keys to sign. So we end up having three signatures. Those three signatures, we aggregate them together. And then guess what? We can do the same thing. We can add on the root and get a tweaked signature. So you have a tweaked public key and you have a tweaked signature. That signature, anyone on the network can show, just like they do now, that this signature is valid for this public key. They have no idea looking at it that these are tweaked or not tweaked. The mathematics works out the same, and that's because of the awesomeness of the linear Schnorr mathematics. But we also have an option. What happens? So if we use our major spending path, which is 3 of 3, this is what we're going to use 95% of the time. On chain, it looks like everything else. You have no idea that this is a complex script, right? If we do decide to reveal a script, and we want to use the third spending condition, which is like wait 6 months and have 1 of 3 plus the lawyer, I believe. How do we do that? Well, it's easy. We just present this hash, and we also present this hash, and we also present this public key, along with, of course, all the stuff you need to fulfill the script. Now, why is that? Basically, when we do this, we're just revealing to the network, aha, just kidding. I actually am using a tweaked public key, and I'm going to prove it to you. So here's the script, all right? All the nodes can take this script, hash it, and then we give them this hash these two together to get this hash, and then we give them hash 1, 2. They can hash these two together to get the root hash, and then we give them the public key, and they can tweak the public key with the root to get the tweaked public key, which is published on chain. So they can cryptographically verify that yes, this script belongs to this taproot address, which is on the blockchain. And then, of course, just like you would normally do, now you, of course, have to prove prove the actions in the script. So you have to verify that it's been 6 months. You got to have your public keys and signatures to do the one of three plus the lawyer, and then boom, you're done. So that is the basic premise of Taproot, is having this ability to essentially kind of toggle between either doing one path of a multi-sig or regular sig that always looks just like a one-to-one pay to public key, but you have the advantage of hiding or hidden within the mathematics near infinite other spending conditions, all in this Merkleized abstract syntax tree or Merkle tree. So this has enhanced its privacy by making the spend all condition indistinguishable from a regular transaction. It allows optional script path to only be revealed if necessary and keeps unused paths private. And it basically makes it so the script size is infinite. I mean, this is how Block and other companies are hoping to build Web 5 or whatever on top of Bitcoin, is because you have an infinitely large Merkle tree. All you need to do is worry about tweaking the root of that tree with the public key in order to anchor it on chain. But you have access to massive amounts of data which can be used to do really robust things off chain. What's this? Oh yeah, so I'll show you the actual math. Right now, the tweak public key I just did, pub key 123 plus the root. In order to spend, we get the tweak signatures, add them together, and then we add the root. We reveal pub key 123 and the root, and we provide appropriate hash leaves and script, which is what I showed. What the tweak public key actually is, it's the public key plus the SHA-256 hash of the pub key and the root, all that multiplied times G. And again, the reason why we don't do plain addition is there's really easy attack vectors, if you can imagine. You don't have to be a mathematician to figure that one out. So we do more complicated math. But I just threw that in there for those of you interested. So here's our Taproot transaction. Again, a visual way to think about Taproot is it's like you got a toggle. You can toggle between N of N multi-sig or public key, or you can toggle over to, you know what, I'm paying to a Merkle tree, a Merkleized abstract syntax tree that has multiple spending conditions. So what about NFTs? Now we understand really what Taproot is and what Taproot does. What about NFTs? Well, if you can imagine, why not just store the hash of the NFT in this tree? Here's my little Mona Lisa NFT, and go ahead and take this image and I hash it and I put it into the Merkle tree. And so embedded within my plain Jane, Bitcoin UTXO is proof that this NFT is actually anchored into the blockchain. And I can prove that because I can reveal all the necessary information. For example, how do you prove it? I've already shown you, but if you want to prove that this image is on the blockchain, you just need to hash it, and then I need to give you this hash, and you can derive this hash, and then I'll give you this hash. You can hash those two together, and then you can get this hash, and then I'll give you the public key, and then you can put those together to get the tweaked public key that's on chain. In other words, in order to prove any image, if you're just doing a hash is on chain, you just need three pieces of information. And you could do that without bloating the blockchain, without storing a whole bunch of arbitrary data. Now, we're going to get into why people are like, well, I want to store the whole thing, or the problems with storing just a hash of an image. So generally on the NFT blockchains now, you do have a hash, not necessarily of the image, but all the metadata. Usually it's the information that points to some type of decentralized server or some L2 that has this image stored, and it kind of points to it like, hey, look, this is kind of the data. Now with ordinals, and the major, use case is like, hey, I'm going to store the whole thing on chain. Of course, this is the problem that Bitcoiners are having, and it's a problem for ordinals. I mean, come on. 4 megabytes is your max size. Like, what if you wanted to do a super high quality image? You're not going to be able to get a lot. Well, Oh, you know what? I take that back. With high quality JPEGs, you could probably still get, a 10, 20 megapixel image within that size range if you really wanted to. But I would submit that there's actually ways where you can actually use the hash of the actual NFT. So for Bitcoin, all we're proposing here is just the hash. All right, and we're not even storing that hash on chain. That hash is actually all metadata embedded within the Merkle tree, which is then tied to our tweaked public key that which is stored on chain. So, what is the problem with storing a hash of an image? If any of you know how hashes work, they literally are absolutely unique to the data set. So if we were to take this image and hash it, all right, if anything changed about this image, if one pixel changed, like this, one little pixel, you'd get a completely different hash. All right. If 1, 0, or 1 is modified in any way, you get a completely different hash. If this was a 10 megabyte TIFF, and you compressed it using high quality JPEG and it looks virtually identical, well, all the data changed. So it would be a completely different hash. So hashing an image, there's a reason why nobody really likes to do that because it's not really feasible. But they're just thinking a little bit too small. Apple developed this thing called neural hash, which I really looked into. And if you go online and look up Apple CSAM white paper, they developed this technology to combat people sharing child porn on iMessage, on iCloud, and everything else. So what neural hash is, it's a perceptual hashing function. So it's a perceptual hashing algorithm. The main purpose of the hash is to ensure that identically and visually similar images result in the same hash. And they actually give an example next. They show you a picture. Here's the hash, and then they take that same picture and make it black and white. Which again, that would clearly gave you a different hash. All the data has changed. You removed all the color, everything has changed. But the neural hash remains the same. And that's because with a neural hash, we're not hashing the absolute data in the image. We're actually hashing a neural engine output, an n-dimensional floating point descriptor that are hashed using LSH, and we're taking the bits and encoding. I mean, we're using hyperplanes. Dude, some really complicated math. Some guys already reverse engineered it and ported it to Python, so you can check that out. He has his stuff on GitHub because, of course, Apple's made this proprietary. But I was just giving you a case in point where, in layman's terms, our Mona Lisa will have a hash. If I compress it, it'll be the same hash. If I brighten the image, same hash. If I darken it, it's going to be the same hash. Black and white, same hash. Totally mess with the colors, throw an Instagram filter, same hash. Really mess with the colors, same hash. Basically, any child can tell the difference, can tell you that all these are the same picture. You're just applying filters. Computers and hashing algorithms are way too stupid because they're not designed to do that. So the neural hash basically does what any human can really do. Even if it's heavily pixelated. Well, what if it had heavily compressed? Same hash. You can crop into the image. Same hash. You could take a picture. Here's a picture of the actual Mona Lisa in the Louvre before it got cleaned beneath the glass. Same hash. You could take a selfie. Your NFT's at an art gallery and, some dodo head is taking a picture with it. You can crop in, boom, same hash. Now, what's not a same hash is this image. This is not the Mona Lisa. This is a different artist, completely different. Again, a human could tell that. The algorithm, since it's based on the perceptual cosine mathematics, all the curves, all the things on a mathematical level that make a picture unique to us visually, this would have a completely different hash. So I'm just throwing that out there. I think that's a much better way to do it. So that way we can just deal with storing just the hash of the image. But if you have to do it the way that the other chains are, whether OpenSea and Polygon and Cardano. I have no idea where people are doing NFTs outside of Bitcoin. They're doing them somewhere, but generally speaking, they're not storing the data directly on chain. So, of course, once you get into real NFTs, like in my opinion, financial documents, digital identity, a land deed, stuff that's just text. That'll be easy to hash and store. So, real quick, what are the pros we have so far? No blockchain bloat. All right, that's huge. Now, of course, the NFT people who are doing this, they don't necessarily care, because they're not worried about bloating the blockchain. Maybe if you're a Bitcoiner and you really get into NFTs, you're concerned about this, but no one else is concerned about this. The base layer transaction fees are literally nil. Your fees are exactly what it would cost to do a itsy bitsy tiny one-to-one taproot address. And remember, this is your address. This has your money. It just happens to have this other information anchored into it. As opposed to the ordinals, you're at the lowest fee possible, you're paying $20. All right. But we all know once the network is busy and the Bitcoin is busy doing Bitcoin transactions, mining these is going to cost hundreds, if not thousands of dollars. With this technology, this is how Taro is going to do it. You don't have to worry about any transaction fees. In addition, you could do quantities. This is just a one for one. Why not mint, this is limited edition Mona Lisa NFT, and you want to mint 100 of them. How can you do that? Well, I'll show you. A protocol like Taro has an easy way to do that. Now, the next big use case, because remember, the only way Ordinals is already out, Inscriptions is out, it's gaining market share left and right. How is another protocol going to unseat that? It has to offer advantages so that the market will choose it. So having really low fees is very appealing, but what's really appealing is this: you can use Lightning. Remember, all this stuff is embedded inside of a transaction and you don't even see it. So the Bitcoin network, those transactions operate just like normal. Nobody knows about the embedded data. Same thing with Lightning. You can move things through the hash time locked off chain Lightning transactions, and you could trade stablecoins, even NFTs using Taro. And you do that by using it at the edges. So if Alice had her stable coin, her Lightning USD coin that she created, and she wanted to send it in a second over to Dave, she can do it over the Lightning network. She would just negotiate with Dave the exchange rate. What is at that second? What is $10 a Bitcoin? Oh, it's this, and that would be the amount that she sends via Lightning over to Dave. So in the best case scenario, it gets over to Dave, and he has the embedded data, where he knows that he got his little Lightning USD. Worst case, if it fails somewhere, or someone tries to cheat, or someone tries to steal, the Bitcoin network has its own fallback mechanism, and he can get a refund for his stablecoin amount. With NFTs, it would be done similarly. You would just agree on, kind of what the rate was, and kind of take it from there. There's a lot of different ways. I'm just kind of giving an overview. Another way is I created a picture, yeah, like this. So your Taro nodes are spread out all over. Taro nodes are, your, I guess, and you could think of it like an L2. Really, it's just a repository of information. So it has all these proofs, all these off-chain proofs, in order to prove that something is stored either on a Lightning transaction or on a Bitcoin transaction. So when you send funds, it's going to go through the Lightning network just like normal, but at your destination node on Lightning, that's also a Taro node or a Taro wallet, and it can convert. So you're moving through the network, whether you're moving through on chain on Bitcoin or moving through Lightning. You're not modifying Lightning. All right, you're not modifying Bitcoin because you've already have the Taproot update, and there's no bloat, so you can't see anything. This is all off-chain data. All right, and this is a Taro input output, which we'll kind of give a brief overview. But basically, it's mirrored off Bitcoin transactions. They actually use like a virtual machine that mirrors like how Bitcoin transaction gets processed. But the input and output addresses, they're not even really addresses. They're just pointers to all this information. So now let's say that Bob wants to send 50 Mona Lisa NFTs to Alice, right? And Bob has his NFTs stuck in here. This is Bob's UTXO. So Bob currently, he's been saving. He's a whole coiner. He's got 1.246586 Bitcoin, all right? So on his on-chain address, which holds the key to all his wealth, and it's hooked up, to his cold card, within that address contains, like we went over, the information to a tree, and within that tree there is represented the hash of the NFT. Well, in order to, let's say, send it to Alice, he would just spend it. He would spend it, and let's say he sends all the funds pretty much to his change address, but he sends like $1 to Alice's address, right? Well, within those trees, he removes his NFT, all right, and Alice gets the NFT. All right, so obviously Bob can prove this fairly easily because he just needs to show the hash of this and this hash. He doesn't need to reveal what he doesn't need to reveal what this script actually says. He just needs to show that the NFT hash is no longer there because Alice could take this as nil, as null, and hash it with this, and then hash and prove that your address no longer has this. But then you have to give up a lot of data, and that's kind of inefficient. But then Alice can also look at her tree, at her address, and see that the NFT is there. And she knows that it's yours because it's anchored to your Bitcoin address. So all the security is coming from Bitcoin, and she knows that you have permission and you have ownership because only the person with the private key can spend on Bitcoin. So since Bob made this transaction and spent it using the private key, then Alice knows that you really were the owner, that you transferred the NFT over to her, and that she can validate that she now has the NFT and you do not. All right. Now, there's no mention of quantity because this is just a super simple explanation. But this is very limited, because the reality is, what if Bob has a whole bunch of NFTs? What if he has 100 NFTs? Pictures, he has, legal documents, he's got spending pass. How are you going to take care of this complexity? Because it's going to get crazy. Well, the answer is don't do it within the mass. Don't do it within the Merkle tree that Bitcoin is using for spending condition. Just go ahead and create a new tree. So Taro goes ahead and creates a whole new tree, and all they do is embed the root of that tree into the Merkle tree, which is all part of the taproot address. So, how does this Merkle tree work? The Merkle tree is actually really simple, which is the only reason why I'm going to go over it because it's not really scary at all. We're going to use something called a sparse Merkle tree. What the heck is a sparse Merkle tree? It has a very interesting property. If you take a hash, now I didn't want to write out a real hash because it's very long, so this is a very short part of a hash. If you take a hash of data that you want to put into a leaf and you convert it to binary, ones and zeros, and then you convert the binary to directions. So if we're going to make one equal to left and zero equal to right. Then literally on the tree, left, 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 right, left. That's where you store the data. So the location of the data in the tree is directly represented by itself, by its own data. Now you're probably thinking like, how is that possible? Well, yes, technically this tree has 2 to the 256 leaves. Now that's unimaginably massive amount of leaves. But it turns out since 2 to the 255 of them are all null, among other things, it compresses down and the tree's not very big at all. But this is a very important property that the location of the data in the tree is a map unto itself. All right. I can give you this hash. You can convert it to directions. You can traverse this tree and find its location. Now, quantities. We're going to go ahead and add quantities on here. This is another type of tree called a Merkle sum tree, where each leaf embedded within it has a quantity number, and that quantity is going to go ahead and feed upwards. So if we take another one, so let's take another hash. We're going to convert that to numbers, and that's going to be left, 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 right, left, left, right, whatever. We're going to just go down here to make it nice and clean. All right, and we're going to put the hash, and we're going to give it a quantity of 10. Well, all these, this one here will have the hash of these two, plus it'll have the quantity of 34. It's going to add those up, and those are all going to propagate up. So just by looking at the root hash, we know exactly what the quantity is of all the items within that tree. This becomes really important later because you want to make sure you have proof of lack of inflation. You know that no one's inflating amounts. So if you combine these together, what you're left with is a Merkle sum sparse Merkle tree. That's what this tree is called. All right, so let's do another item. Convert it to binary. We're going to do left, right, right, left, and we're going to go ahead and put 16 in there. All right, so we put 16, and they're going to traverse up, and then 34 plus 16 is 50, and then all these numbers get updated. All right. So let's say, for example, this could be a whole branch of NFTs. This could be the Louvre, the French Museum NFT collection. And I could have 24 Mona Lisas, 10 of the Seated Scribes, 16 of St. John the Baptist. These are all famous artworks within the Louvre. And they're all represented in a way where I can prove definitively that I'm not cheating numbers, that I'm not. Let's say, for example, I'm going to give you all 24 of my Mona Lisa NFTs. Well, you can look at this tree, and just by looking at the hash, you can confirm that that hash is no longer there, that it's null. But you can also confirm the quantity. If I were to remove this, then this amount right here would be completely updated. So would this amount be updated? So would the root. But it's also isolated, where if you can imagine having hundreds of NFTs, you want to maintain the privacy of all your other data, because these trees can grow massively. So this gives you the proof of assets, proof of basically proof of assets, and proof that you're not inflating amounts. Here's another Fun Bucks coin. This is the one they actually put in the specs, and this is like a stable coin. All right, so this would be on its own branch, and it would have its own breakdown. This one I only bought 78 worth, whatever that is, and so I update the quantity up here to 128. So this is actually what's now stored in your transaction. So now, if you could imagine, now when Bob wants to wants to send 50 Mona Lisa NFTs to Alice, now he goes ahead and sends all the change to himself, and he sends, in this case, he's sending some dust, whatever, $1 to Alice. Now they can both look at their trees and they can confirm. So Alice knows, because she knows what the original tree looks like. She can see that you pruned off all your Mona Lisa stuff, or your Louvre. I changed the example, but I didn't update the pictures. She can see that all those are pruned off. She can see her tree. She can see that she now has 50 of the Mona Lisa NFTs, and she can verify the security of all this, because you're not trusting in some random new blockchain, you're trusting in the Bitcoin chain. All this metadata can be provably linked within these addresses, and the authority, Bob has full authority to show her that he's the true owner, because only he has the public key to go ahead and spend. So that's essentially how it's working. So, an overview, we know Bob is the owner of the UTXO, since only the private key can sign to spend the transaction. We know Bob is the owner of the input address, since the address directly references the UTXO and has the proof needed to reveal its Taro script. Only Bob will be able to spend the UTXO on the blockchain, proving his ownership of the input. And again, this address just has a whole bunch of data that then points to where the Genesis block is on the blockchain, and what the data is that we're looking for. We can verify the amount spent by making sure the amount is less than the input being spent. Alice can verify that Bob's amount is sent by checking the new tree and verifying the values no longer exist. Additionally, she can check her newly created branch to ensure she has possession of the NFTs. She can also verify Bob's assets moved by viewing the root amount of Bob's tree. She has no visibility on Bob's other assets since he has not revealed any proof of those. On Bitcoin, one can verify the validity of any spent transaction by tracing it backwards all the way to its Coinbase transaction or Genesis transaction. And the Genesis is where is the first time that you introduce it in a Taro tree. Each Taro transaction input has a corresponding previous output, which reveals a Taro tree which has the previous state of all the assets. So again, on Taro, you have an input and an output, and then when you spend it, you have an input and an output. The input is just referencing the output. The output information is just pointed, But really, what's happening is this information is just referencing these offline trees. So these are just proofs. They're proofs that are anchored into the security that Bitcoin provides because everyone knows that no one could modify this information because it's secured by the proof of work. And everyone knows that in order to move and modify that information and create a new transaction output, you need to have the private key. And I'm going to skip over this for now. But that's basically a general kind of overview. No bloat to the blockchain. Of course, if you do a neural hash, it's really easy to store just a hash of your image within this data. And that way, because remember, the issue was never I don't have a way to securely store my picture. That's been solved, whether it's by Dropbox or Google, or you could store it on your own decentralized drive, or you can put it on an SD card or a hard drive. The issue with NFTs was never about the preservation of data. I don't know if anyone thinks the government's going to go and try to wipe out your pudgy penguin and go to everyone's computer and erase it, and go to all of the decentralized servers and try to compel them to erase your image. That would be silly. It'd be much better that you would be able to keep your own copies and trust in your own redundancy. The key with NFTs is proving ownership. It's proving that this is unique and that this is yours. With this, we are doing all this. Now, I believe that this will inevitably destroy or majorly limit inscriptions simply because it's superior. It's superior in the sense that it's no bloat, that it's super cheap. You never have to worry about paying hundreds of dollars because it's literally no data. You could do it on Lightning. So you can send these things instantaneously. You can literally convert them on the fly in Lightning, where you could send one stable coin and someone could receive an NFT. You could send one stable coin over Lightning and someone could receive a different stable coin. You could send groups of NFTs and someone could receive a completely different NFT. And you could literally be destroying and creating these on the fly by negotiating exchange rates. I mean, it's literally off the charts, the stuff you can imagine doing. And of course, Web3 is going to function pretty much the same. Not Web3. Web 5 is what they were trying to call it, right? I think. Again, having all this data that's just anchored, and all the Bitcoiners on Twitter, they're not freaking out because they're looking at the blockchain and hey, everything looks normal. But you literally can have a whole layer two with simply data that's anchored in by taking a Merkle sum sparse Merkle tree and embedding the root inside a Merkleized abstract syntax tree and taking that hash and tweaking it with a public key. That concludes my explanation of Taro and Taproot. Hopefully that gives you some insight.